The question is, let me say this is V2. What is the quiescent output voltage? Okay. And there is zero input, zero differential input. Okay. So let's imagine that V out is greater than V2. So what does it say about currents of M1 and M2? M1 and M2 have the same gate voltage and the same source voltage. Okay. So if V out is greater than V2, how will the current in M2 compare to the current in M1? No, there is channel length modulation. Yeah, it will be more. How about M3 and M4? M3 and M4 also have the same gate source voltage, but the drain voltages are different. So if V out is more than V2, which one is greater? Current in M4 or M3? M3. So that's an inconsistent condition, right? So this says that the current in M3 is this. So this voltage is more than this voltage, so the current here has to be more. But if you look at the upper transistors, this voltage is less. Okay, and I of M2 has to be equal to the current in M4, and current in M1 and current in M3 are the same. Okay, so the only condition that gives you consistency is V out equals V2. Okay. Which one? No, it's not a question of stronger. This is exactly equal to this. That you agree? Huh? So similarly for the other one, the current in M1 and current in M3 are the same, right? So you can't have inconsistent conditions there. Okay. Let's get back to making the op amp using the differential pair. What we did was to start off with a resistor here. Then we calculated the gain. It comes out to be something, but with the available supply voltage, the possible value of gain is very small. Even if you increase the supply voltage to 10 volts, you will not get a huge amount of gain. You will get in the hundreds. Okay. So especially with the low supply voltage like 1.8 volts, the maximum gain we calculated to be around 16. So this is not a useful technique. So we decided to replace this with a MOS transistor, which can carry the same current, but give you a much higher resistance in the incremental sense. Okay, it gives you a much larger resistance. In quiescent condition, I naught by 2 has to be flowing through that, and perhaps a convenient way of getting that I naught by 2 is by mirroring this one. Okay. So just like I discussed a couple of minutes back, in absence of any mismatches, this output voltage will be equal to V2, which is VDD minus VGS3. So M1 and M2 are identical, M3 and M4 are identical. So the quiescent output voltage is VDD minus VGS3. Now, I can think of this as a transconductor or a voltage amplifier. I can open circuit the output and think of it as a voltage amplifier, or I can short circuit the output, measure the current, then I am treating it as a transconductance. When I want to measure the parameters of the transconductance, I need to terminate the output in an incremental short circuit. Okay, when I want to measure the output current of the transconductor. What will I connect in the large signal picture? Huh? Yeah. So what value? What's the value of the? So if I connect this to, this would be at VDD minus VGS3. Okay. I connect it to a voltage source of value VDD minus VGS3. Let's assume that somehow I have measured this or calculated it and I connect it there. So this will not disturb the bias condition in any way, but it will terminate the output with an incremental short circuit. Okay. Is this clear? So I do this, then I can measure the short circuit output current of the transconductor. I can measure the output resistance of the transconductor. Then I will have everything I want to know. Okay. Then I can go ahead and calculate the voltage gain if I want to. Right. So first let's calculate the transconductance. That is, I excite the input with a small differential increment. And I want to calculate the incremental current I out. How do I calculate this? How much is it? How would you calculate this? How do you go about calculating this? Huh? No, I know, but how did you calculate that? Yeah, but that analysis is not easy, right? What is this voltage? Yeah, but the circuit is not symmetrical. So technically that's not a correct thing to do. Okay. This circuit is no longer symmetrical. It's not like when we loaded the differential pair with two identical resistors. It's not exactly symmetrical, so we cannot say that the tail node increment is 0. Okay. So what I'll do is but it is 0 in some conditions. It is close to 0. It's not exactly 0. Okay. If you calculate that problem in the assignment, which has the differential pair terminated by two different resistors, R1 and R2, you will find out exactly when the conditions under which it is 0. Okay. In fact, that's also the reason why I chose to do it like this, meaning I calculate the output short circuit current, then I calculate the output resistance, and from the two I calculate the voltage gain. Okay. So in this case, it turns out that this Vx is approximately 0. Okay. But if I try to open circuit the output, if I leave it open, if I don't terminate it with a voltage source, this point will be very far from 0. It can be very far from 0. Okay.
Also, we can assume that node voltage could be something Vx and then calculate the current that is flowing at out.
First of all, that is very much true. You can put the entire incremental circuit and analyze the whole thing. You will get the right answer. Okay. In fact, you can do it as an exercise. Here I will choose the slightly simpler route. I will assume that Vx is 0 for now. Okay. And it turns out to be true. Vx is approximately 0 when I short circuit the output. Okay. And the conditions can be evaluated by solving the problem in the assignment. Okay. But in general, it's not true. So you will see that let's say it's terminated by two different resistors. Okay. So in general, it's not true that Vx is 0. Okay. Now there is one condition under which Vx is 0. That is, if these two transistors have 0 output conductance. Okay. If both M1 and M2 have 0 output conductance, then Vx is approximately 0. Okay. So this is a bit of hair splitting, but I think especially the first time you are looking at the circuit, you should go through it rigorously, understand all the approximations under which certain things hold true. After that, you can probably bypass some of those things. But just by looking at the circuit, I cannot say that Vx equal to 0, and it is not 0. Okay. That's what you solve the assignment and find out. Okay. So if you look at the tail node voltage, Vx equals 0 if the circuit is symmetric and you apply a purely differential input. Okay. Now Vx is also equal to 0 for asymmetric loads if GDS1 is 0. Okay. Is it clear how this comes about? One thing is, when we analyze the differential pair for differential signals, we assume that the current source at the bottom is ideal. We assume that it has no output conductance. And again, that's a good enough approximation. Otherwise, you will end up with a mess of equations, which you can certainly solve. Okay, but the result will look so complicated that it will mask the real solution. Okay. So we'll assume that whenever we are analyzing the differential picture, that is, when we excite the inputs differentially and measure the output, we will assume that the bottom current source is ideal. Okay. So now, if you have GDS1 to be 0, the picture you have is this. So this is incrementally Vd by 2 minus Vd by 2, and this is some Vx. And if the current source is ideal, this is an open circuit. Okay. So what does this mean? Gm times Vd by 2 minus Vx plus Gm times minus Vd by 2 minus Vx. The whole thing equals 0. Okay, and the only solution to this is Vx equals 0. Okay. Now you can't do the same thing if you have GDS. Okay. So if you have GDS, Vx will be 0 only if these two voltages are also, this is some V2 and this is minus V2. Okay. Only then will be Vx be exactly 0. So we can make either this assumption, or in fact Vx is approximately equal to 0 for certain conditions on the load. Okay. Even if the loads are asymmetrical, the value of Vx is very close to 0 for certain conditions on the load. So we'll assume that one of these two is true. Okay, and it is true. We'll discuss that afterwards. But we'll assume that Vx is very close to 0 and go ahead with the calculations. Okay. So incrementally we have this picture. And this is an open circuit. And this is terminated in an incremental short. Okay. First of all, let's analyze with all GDS to be 0. That's very easy. Okay. So what is the answer then? This is the tail node is 0. What is the incremental current flowing here? It's GM1 times VD by 2. Okay. And here it is upwards and GM1 times VD by 2. And this GM1 times VD by 2 gets mirrored by this current mirror. Okay. Or if you want to calculate it further, what is this voltage? What is the voltage at this point? It is minus GM1 by GM3 times VD by 2. It got a little cramped there, but it's minus GM1 by GM3 times VD by 2. Okay. So what is the current induced by GM3 here? That this voltage appears across the gate source of M4, which is this transistor. And that gives you a current GM3 times this entire thing, which gives you GM1 times VD by 2. Okay. So the output current will be GM1 times VD. So the transconductance of the differential pair with the current mirror load is the transconductance of the one of the input transistors. Okay, in the quiescent condition. Now, what's the result if I include GDS to all the transistors? What will happen? I'll write the equivalent circuit again. So this is an open and tail node is at 0 approximately. And this, the diode connected transistor looks like a conductance of GM, right? And it has its GDS in parallel with it. And similarly, I have another GDS3 here and GM3. Okay. This is incrementally ground and the output is also incrementally grounded. So what's the result now? What is the current through this conductance? 0. The Vx is 0 and the output is also at 0. So it is approximately, it is 0. So this is not in the picture. What about this one? That's also 0. Okay. So what is the current induced in this transconductance? Huh? GM1 times VD by 2. What is the voltage here? So the only difference from the previous case is that you have GDS3 and GDS1 added to GM3. Okay. So this voltage is minus GM1 by GDS1 plus GDS3 plus GM3 times half of VD. Okay. So now the lower part of the current here remains the same. So this current is GM1 times VD by 2. Now the current pushed in from the top is slightly different. That is GM1 by GDS1 plus GDS3 plus GM3 times GM3. Okay. This is the total current that comes out. Now clearly this ratio is approximately 1. Okay. So if you look at this part, this is close to 1 but not exactly 1. So it reduces the transconductance slightly, that's all. So there is some current through M1 and that gets mirrored, and the mirroring ratio is not exactly 1 because of the output conductances of the transistors. So there is 1/2 of the current coming directly from this transistor and the other one is not exactly half, it is slightly attenuated. Okay, that's the only difference. Is this okay? So in presence of GDS, the transconductance is so it's GM1 times this whole thing, which is close to 1 but not exactly 1. Okay. But for all practical purposes, you can assume that the transconductance of differential pair loaded by a current mirror is the transconductance of one of the input transistors. Okay. Now you can do the analysis with everything combined together. You just put the 3 node equations and do it. You will get the same answer. Okay. So once the circuits start becoming complicated, you have to make some judicious approximations. But of course, you can always go back to the brute force analysis and do the analysis. Then you should interpret it correctly and then see what those approximations are and if they are valid. Okay. So we have the transconductance. What is remaining to be calculated? The output conductance. Once we have that, the picture is complete, the DC picture. Right. Now to calculate the output conductance, what I can do is, I have this quiescent voltage, VDD minus VGS3. To that, I add an increment, V test, and I measure the increment in the output current. The quiescent current anyway was 0, so I measure the current I test and find out the output conductance. So what is the output conductance of this? Output resistance of M4 in parallel with M2. So the output conductance is GDS1 plus GDS3. Okay. I mean, GDS1 is the same as GDS2 and GDS3 is the same as GDS4. Is this the answer? Does everyone agree with this? Huh? Well, yeah, we'll see. Okay. So obviously you don't agree with this answer. So you don't agree with this answer. Okay. What is your answer? So this I test you can divide into two parts, right? I1 and I2. What is the conductance contributed by I1? GDS3 or GDS4. Okay. So I assume that the circuit is symmetrical, right? I assume M1 is M3 and M1 is the same as M2 and M3 is same as M4. So I will always use GDS1 or GDS3 to denote the small signal parameters. Okay. So you are saying it is GDS3 plus something else that we need to calculate. Is that correct? There is some conductance contributed by I1, something else contributed by I2. Okay. So let's see. We will calculate what is contributed by I2. Now this current source is an open circuit. We assume that it's ideal. What is the impedance looking this way? Here. So it's a common gate amplifier terminated by some low impedance. Okay. If the load impedance is very large, then it's not 1 by Gm, but in this case, the impedance here is also very small. Okay. So this is very close to 1 by Gm1. So what is the impedance looking down into this transistor? So the picture we have is, we have M2 and M2 is connected to an impedance of 1 by Gm1. So what is the impedance looking in here? 1 by GDS2. So what is that? It will be a cascade. So what's the answer? 1 by. So see, the output impedance of the common gate amplifier was, if we had some resistance in the source and some Gm and GDS, you are saying it is Gm divided by GDS 1 over Rs. Sorry, times Rs. Is this correct? So actually that is important. There are other terms also. The output conductance of this is Gm by GDS times Rs plus 1 over GDS. So what is this term in our case? What is the first term? So Gm times Rs is 1 in this case. Okay. So this part is 1 over GDS1. Okay. And what's the next one? That's 1 over Gm1. And 1 by GDS is nothing but also 1 by GDS1. Okay. This part we can ignore. 1 by Gm1 in comparison with 1 by GDS1. Okay. So the impedance looking down here is 2 by GDS1. Is this okay? All I did was to apply the formula for the cascade amplifier, and in this case the resistance which is degenerating the source is not very large. It is the same as the transconductance of the transistor. So this multiplying factor Gm by GDS is not a very large number like it would be in a normal common gate case. In this case the multiplying factor is exactly 1. So because of degeneration you get GDS1, and because of its own output conductance you get another GDS1. It is 2 GDS1s in series, which gives you 2 by GDS1. Okay. Is this clear? The impedance looking down into M2, that is, if you look at I2 will be V test times GDS1 by 2. Okay. So what is the output conductance of the differential pair? Huh? What is the output conductance of the differential pair? So now the answer has changed to GDS 1 by 2 plus GDS 3. Is this correct? What is the incremental current I1? So this I2 which flows here, this is an open circuit. Okay. So this flows into the current mirror, it also appears here. Isn't it? This figure has become unbearably messy, so I'll draw it again. The summary of the discussion so far was that looking in here we have 1 by GM1. Okay. Looking into the source of M1, you have 1 by GM1. These are incrementally grounded. So because of this degeneration, looking into the drain of M2, you have approximately 2 by GDS1. So if you apply an incremental voltage, we test the current that flows here is V test times GDS 1 by 2. Okay. Now that current, it flows like this. It flows through M2 and M1 and finally into M3. Okay. So that gives you, if it flows into M3, it will also flow into M4, right? Because it's a current mirror. It's a current mirror for large signals as well as for small signals. The mirror ratio is not exactly 1 because of output conductances, but we'll approximate it to 1 just to avoid complicating the algebra. Okay. So this gives you a current of V test times GDS 1 by 2. Okay. That is because of the current mirror. Additionally, you have the output conductance of M4, which is GDS 3. So that gives you a current of V test times GDS 3. Okay. So if you apply V test here, certain current goes down and certain current goes into M4. The incremental current through M4 is V test times GDS 3, which is what you expect anyway, simply because the output conductance is there, plus V test times GDS 1 by 2, that is because of this loop. Okay. And that through M2 is V test times GDS 1 by 2. So the output conductance in fact is GDS 1 plus GDS 3, but with a slight twist to the story. Okay. Is this okay? So if you don't do any analysis, you are right. If you do halfway through the analysis, you are wrong. And if you do the full analysis, of course you are right. Is it okay? Again, you can put all the node equations with everything together, calculated, you will get something very close to this. The only approximation we have made, there are two approximations we have made. First of all, looking down here, it's not exactly 2 by GDS1. It is 2 by GDS1 plus 1 by GM1. So again, that's very good approximation to neglect that 1 over GM1. And secondly, when this current flows here, not all of it gets mirrored. Okay, because of the output conductance of M3. So that's again, that's also a good enough approximation. So this is by and large right. Okay. So far we know that the transconductance is GM1, output conductance is GDS1 plus GDS3. So the open circuit voltage gain and this is the DC gain that you get if you operate the transconductance with a capacitive load. Okay, this is GM1 by GDS1 plus GDS3. So it is again similar to the open circuit gain of a common source amplifier, right? It's of the order of GM by GDS. Now you also have GDS3 because of the presence of the active load. But the situation is much better than if you had connected a linear resistance as a load. Okay? Because now you can increase GDS1 and GDS3 without increasing the supply, simply by increasing the length of the MOS transistor. Okay? So to have a large DC gain, you have to use long transistors. I mean, you have to use long transistors for both NMOS and PMOS, because if you have a situation where one of them is dominating over the other one, it's not all that great. You have to reduce both of them to increase the DC gain. Okay? So just by keeping exactly the same current and going on increasing the width and length in the same proportion of all transistors, you will go on increasing the DC gain of the amplifier. What is the disadvantage of that? Parasitic capacitance. As usual, if you try to increase device size, you will increase parasitic capacitances. Okay? Probably not. If you have not simulated any circuits at all in that particular technology, it's hard to do. And generally calculations of lambda, etc., if you look at it, lambda is not even given, right? It's hidden in some many parameters. But usually what happens is you will start playing with some technology. So let's say you make an inverter which is made out of minimum size transistors. If you plot it, you know what its slope is. So you roughly have an idea of the GM by GDS of the minimum length transistor. Okay? So now we want a GM by GDS, let's say, which is 10 times that. Then I would go and make the length 10 times. That's, if you have no information about technology, it's hard. But if you have something, then you can scale up based on your experience. Okay. And even if you have not played with it, you can of course start doing it. That's not a big thing. But you can take some arbitrary length. Okay, let's say you get this has to be 100, right? First of all, if you have simulated any inverter at all, you will know that a minimum length device will not do this. Okay, a minimum length device will probably give you a gain of 20 or something of the sort in this technology. If you go to more fine line technologies, it will be even smaller than that. So maybe, but I don't know anything else about the technology. So I'll just start with perhaps some, let's say length equals 1 micron in this technology. And then I'll adjust it to some overdrive, the overdrive with which I intend to operate in the given scenario. Okay, something like that, maybe overdrive 150 or 200 millivolts. And then I simulate the GDS once. Once I know that, I'll know whether to increase the length or decrease the length, where to stop, etc. Okay. So although, I mean, given lambda and so on, you can calculate it in closed form. It's not very useful. In fact, the way I would calculate lambda is by going and simulating a transistor and looking at the value of lambda. Lambda is not something that's given to you by the process boundary. It's a combination of different parameters because of different phenomenon that happens in the MOSFET. Okay. Any questions on any part of the analysis or the answer? Okay, so we have calculated the differential transconductance and output conductance and the DC gain. So the first method of increasing DC gain is to increase the length of all transistors. But if you are at a DC gain of 50 and you want to make it 5000, it's probably not going to happen with increasing the length of transistors, right? Because simply you can't increase the length by such a huge factor. First of all, it will give you very large parasitics, and simply the device area will not be feasible. It will be too expensive. So what else can you do? Huh? So we'll have to use current buffer. So somehow what we see is that looking down here you have some impedance, and looking up you will have some impedance, and both you have to increase. Okay, and we will have to use some current buffer or a common gate structure to improve the output resistance. Okay, we will look at that later. That will give you another type of op amp. Okay. So, but before going into that, let's evaluate some more things about this op amp. And once you calculate for one in great detail, for the rest it will become easier. Okay. Any questions on the DC analysis so far? So one of the things I said was important about an op amp is the common mode. Yeah? Huh? Yeah. No, I said 1 by GM1 is very small while calculating the impedance here. No, but this voltage is not 0. When you excite it with an incremental voltage V test at the output, this voltage is definitely not 0. Okay. What is it? What is the value there? Huh? Yeah, it will be something. It's certainly not 0, because if it was 0, then you would not get any feedback from this side. Okay. What's that? Yeah. So you will get the same answer anyway, because if I analyze it as two separate amplifiers, then what happens is that looking down here you get GDS1 and looking up you will get GDS3. Okay. So I mean I think whatever value of impedance you have here, if you have feedback here you will get the same answer. What I mean is this. Oh. Let's say I have this one, and now this is not biased with the current mirror from the other side. Okay, it's biased with, let's say it's biased independently. So if it is biased independently, if I apply an increment V test, I get something here. Okay. So that will be V test times GDS3. So now because you are feeding it back, you get GDS1 by 2 here also. Okay. But let's say I connect some resistance in series here. That is, I make the looking in impedance look higher also, right? And that means that looking in here also you will get higher impedance. Okay. So what will happen? You will get V test times GDS3 here, and this will not be GDS1 by 2. It will be some G1. Okay. And looking down here also you will get G1. So you will always get V test times GDS3 plus 2 times G1, where G1 is the impedance you look in here. But that does not have to be exactly equal to GDS1. Okay. Because if I deliberately connect some resistance here, that will not be the case. Was that the question? Does it always come out to be GDS1 plus GDS3? Yeah, that's because of feedback, but I can create an artificial situation where this is. So for instance, there is a class of circuits where you do degeneration here. Okay. You degenerate the differential pair. In that case, you will get mostly GDS3, that's all. The rest of it is negligible. Okay. So, but whatever conductance you see here, you will see an equal amount of conductance on the top also because of mirroring. There is feedback like this. Okay. Anything else? So, one of the things I said was important with an op amp is the common mode gain. Okay. We want it to be low. I mean, that's, in that sense it is important. So, what is the quiescent output voltage again? So, in absence of any asymmetry, it is VDD minus VGS3. Okay. And let us say it is in the quiescent condition. What do I mean by common mode gain? I apply an equal increment, that is in phase increments to the two sides, and look at what the output increment is. Right? So, what do you think it is? How much is the common mode gain of this? What's that? Yeah, that's correct. 1 by GM3. Anyway, let's see. How would you go about calculating this? What happens if this is an ideal current source? So, in that case, see, because of symmetry, this current I0 will have to get divided equally between these two. Okay. And if I0 doesn't change at all, then this is like driving M3 and M4 with ideal current sources. Okay. So, the output voltage cannot change. So, if these currents don't change, it's like having this picture. Okay. This is I0 by 2, this is I0 by 2. So, whatever the output voltage is, it will not change for sure. Okay. So, if the tail current source is ideal, the common mode gain is 0. So, in fact, one of the things that you will have to do if you want to improve the common mode situation, that is, if you want to improve CMRR, is to improve the tail current source. Okay. Now, let us imagine that it is not an ideal source, then we have to calculate the common mode gain. So, in the quiescent condition, in absence of the increment VCM, you have I0 here, I0 by 2 and I0 by 2 in the two branches. And also because of symmetry, whatever be the increment VCM, as long as the same increment is applied to the two sides, this voltage here, this has to be equal to this. That we have already reasoned out, right? If that's different from, if the left side drain voltage is different from the right side drain voltage, you will get an inconsistent condition. The NMOS analysis will say that one current is more than the other, and the PMOS will say the same thing is less than the other one. So, the two have to be equal. So, this we already know. All this makes the analysis very easy. Now, we will say that this is M0 and this has an output resistance of, output conductance of GDS0. Okay. So, in the quiescent condition, let us say that the current is I0 and it divides equally between the two sides. Now, a small signal increment is applied to both of the sides. So, what is the voltage at the tail? Huh? What is the voltage at the tail node? It should be the same. Okay, we'll assume that the bulk of the NMOS is connected to the source. Okay. So we have essentially a source follower between the gate of these transistors and the source. Okay. So the increment here will be the same, VCM. Okay. So what is the increment in the current? Increment in the tail current? Huh? So it is just VCM times GDS0. And what will be the current on the left and right side? Huh? They have to be equal, right? So this increment also gets divided equally. So VCM times GDS0 by 2, and this is also VCM times GDS0 by 2. Now in the quiescent condition, this node was at VDD minus VGS3, whatever the value of VGS3 is. Now the current has increased by VCM times GDS0 by 2. So what is the increment in the voltage? So that incremental current divided by incremental conductance at this node, okay, which is, and it's in the opposite direction, okay, VCM GDS0 by 2 times GM3. Is it okay or no? So I have this transistor M3 here. And I had a certain current flowing I0, and it changed to I0 plus VCM GDS0 by 2. So whatever voltage was here, quiescent voltage, it will change by VQ minus the current increment divided by GM3. Okay. So the red parts here are the increments and the black ones are quiescent quantities. Okay. Now we also know by symmetry that this voltage and this voltage are the same. Okay, they have to be the same. So this will also change by minus GDS0 divided by 2 times GM3 times the input common mode increment. So this is the change in output voltage in response to a change in the input common mode voltage. So the common mode gain is common mode gain is GDS0 by 2 times GM3, and the obvious way of reducing the common mode gain is reducing the value of GDS0. Okay. How would you do that? So again, first you can try to increase the length if you are interested in only the DC quantity. Then if you increase length and width by a large amount, that will increase the parasitics. So you can go to a cascode current source. Okay. So this common mode gain is very small. In fact, not only is it smaller than the DC differential gain, it's also much smaller than 1. Okay. And the differential gain was GM1 by GDS1 plus GDS3. So the common mode rejection ratio is the ratio of the two, which is very large. Okay. Any questions? What will be if we had used physical resistors instead of, you can think about these two problems. Firstly, we have linear resistors instead of MOS transistor. What is the common mode gain of this? And secondly, this is actually somewhat interesting. What is the common mode gain if this is biased independently? Okay. So let's say this is I naught. This is I naught by 2. Okay. You set it up so that in the quiescent condition all the bias points are fine. After that you apply an increment to the common mode. Then you look at the output increment and see what that's going to be. Okay. So the main difference between this and what we analyzed is that this is not connected to this node, but it's biased from an independent source of I naught by 2. Okay. So I think the next we'll meet will be the next week, right? Next Monday. Friday is a holiday? Yeah. Okay. Have fun tomorrow and also in the weekend. Until today.